Hello everyone. In today's video we will be looking at this amazing integral, which is the Gaussian integral without the polar coordinates. We will be looking at an easier version of the solution, which is without the polar coordinates, because if you use the polar coordinates it will lead you to Jacobian matrix, and it really requires a complex analysis and some analogy knowledge. So let's see how this will go. By the way, this is the first video of this channel, but I would like to inform you that actually I have another channel which based in Turkish, and it has, I don't know, maybe 200 videos, I don't know. But it's all Turkish and it's for all the Turkish students. But I would like to make a lot of videos in English and, make mathematics with global people. Okay, so let's see how this will go. So we have this non-elementary integral, which is we don't know the antiderivative of this function, which is the error function. So we will be using some really nice techniques for evaluating this integral. So let's write the question again. So the integral minus infinity to positive infinity e to the power of minus x squared dx. Okay, so let's note that, note, e to the power of minus x squared is an even function on R. We know that on R, e to the power of minus x squared is an even function, which means e to the power of minus x squared is equal to e to the power of minus x squared. So actually we can write this integral like this: 2 times 0 to positive infinity e to the power of minus x squared dx. Okay, no problem from here. So what can we do now? As you all know, many people goes like this. This is equal to 2 times 0 to positive infinity e to the power of minus y squared dy. Okay, so I just write y instead of x. That changes actually nothing. If you draw a 3 here and 3 here, that would change nothing as well. So what can we do here? Okay, so this equals to I and this equals to I. Let's multiply them and let's calculate I squared, which is 4 times 0 to infinity and 0 to infinity e to the power of minus x squared plus y squared dx dy. Okay, so we were struggling with one variable integral and we have double integral. We have actually more challenge right now. So what can we do from here? Okay, this is, how can we say this? This is the point that we will go a different way. So many people says x is r cos theta and y is r sin theta, and this is actually a polar coordinate. Yeah? And we have to write this dx and dy as dr and d theta. And this is not actually that easy. We have to, write a Jacobian matrix and calculate the determinant of those matrices. And we have to change this dx and di as dr and d theta. And this is a lot of work for calculus 1 and 2 students. So what can we do? What can we do is we will go with the Lagrange method, which is actually changing the variable. Let's say y is actually equal to x times t, and x here is just a constant, not a variable. We are changing the variable to t world, not x world. So if you differentiate both sides, you will have dy and x dt instead. Okay, I can do this. This is, how can we say that? This is legit. Why? Because actually we are just saying y over x is just equal to t constant. But actually this t here is a variable. That's legit, and there's no problem with this. Okay, so let's write this down, what we accomplished here. This is I squared is equal to 4 times 0 to infinity. What are the boundaries? It's the same, 0 and infinity, because if you put y to 0, then t must be 0, and if you put infinity to y, t must be infinity. So boundaries hasn't changed, but this e to the power of have changed, which is e to the power of x squared times 1 plus t squared dx x dt. Okay, that looks good, that looks better, but we have a problem. What is that? This x is not in here, it's outside. If I can put this x in here, then the world will be a better place for us. But how can we do that? Actually, we can put this x in here. In what excuse? Because this function is smooth convergent in 0 to infinity interval. What is a smooth convergent? Actually, it's an analysis tree topic, but actually, if you look at this notation, I think you will remember. This is a smooth convergent function, so we can take this x in here. This is a theorem, of course, we have to prove it, but this is not our job for now, so we will use a lot of theorems in this solution without proofs. If you want, I will make another videos of these proofs later. Okay, so let's put x in here, and what do we have? 4 times 0 to infinity, 0 to infinity, e to the power of minus x squared plus times 1 plus t squared x dx dt. Okay, now the world is a better place, of course. Why? If you say u to this, if you use the u substitution, then the derivative of this power is here. So actually, this is not non-elementary integral. It's actually pretty easy. So let's say this integral, let's say this is I2. And let's calculate this and put this in here. Okay, so I don't have any space now. Okay, let's erase this. And let's take this boundary. Okay, so what do we have? We have I2 is equal to 0 to infinity, e to the power of minus x squared times 1 plus t squared x dx. So let's use the u substitution here. Let's e to the power of x squared times 1 plus t squared is equal to u. So let's differentiate both sides. We know the exponential function derivative. So this here is actually the same. And we have to take the powers derivative, which is minus 2x times 1 plus t squared dx is equal to du. What do I need? I need x dx because I have x dx right here. So I have to find the x dx is what in the u world. So let's take this alone, which is x dx is equal to du divided by minus 2 1 plus t squared divided by this. What's this? This is u. So u here. Okay? So we don't have any problem right now. What happened to the boundaries? If we substitute 0 in here, you know, u is just 1. If you substitute infinity here, u is just 0. But no, actually 1 to 0, actually it's not that cool. What can we do? We can do this. We change the boundaries, not 1 to 0, let's say 0 to 1, and make this negative a positive. So we can have a deal. So what do we have? Conclusion, I2 is equal to 0 to 1, which is 1 over 2, 1 plus t squared. We have u right here, but do not forget the u bottom here, u du. Okay, so this is nice because these u and these u are cancelled out. And we know that this is just a constant for u world. So this integral's conclusion is just 1, because this is actually not different but this, right? And this is 1 and this is times. So this integral has 1 over 2 times 1 plus t squared answer. So we calculate the I2 integral and we find 1 over 2 times 1 plus t squared. Okay, so let's substitute this answer to here and knock ourselves out. Okay, so I am erasing this and saying 4 times 0 to infinity this 1 over 2 1 plus t squared dt. Okay, so let's make as a deal. I will erase this 2 and I will make this 4 a 2. Okay, good. Is it look familiar? Yes, it is. This integral is a very famous integral which is arctangent t. Okay, so this integral has a solution which is arctan t 0 to infinity. So if you substitute infinity here, we have pi over 2 in here, and times 2 is just pi. If you substitute 0 in here, the answer is just 0, and we have pi. But what's pi? Pi is I squared. But what do I find? I have to find the I. So let's square root of both sides. And conclusion, I is just equal to the square root of pi. So we calculate the integral and we find the answer, which is square root of pi. So actually, you don't see this integral like this. Many of you maybe see like this. 0 to infinity, e to the power of x squared dx is just equal to square root of pi over 2. This is more famous, but this is actually pretty much the same. Okay, so this was actually an hard integral, but we solved it an easier way, which I said is Lagrange method. By the way, if you want to look a proper solution of this, a Black Pen Red Pen's channel is a perfect place for it. You can search it on YouTube or Google. You will find a better video of this. I just want to make a video and put it on my channel. Maybe some people see it and learn something from it. Okay, so that's it for the first video. Thank you for watching and see you on the next ones.